Okay, so we're going to look at some pretty important laws today that have to do with logarithms. Like exponent laws that you do in grade 9, multiplying powers with the same base, you add the exponents, that kind of thing. And a lot of these laws, as you would expect, are very similar, so easy to remember. And some of these you've kind of already done, but we're just going to, I guess, examine them again. Like this one's really quick, but we're still going to look at it. So how would you, like if you didn't know what the answer to this was, I think a really good trick is always, well, rewrite it as an exponent. So I would do something like this. And maybe I would just do this like off on scrap paper or something, right? Equals A, like that. So what you have been doing is probably putting an x in here, and then a to the x equals, but today I don't want to do it that way. I just want to do this like thinking. And so, well, this is a to the 1, so this would have to be a to the 1, right? So the log base a of a is 1. And then I hope I don't have to say this, but obviously the a is supposed to mean any base. So log base 2 of 2 is 1. Log base 5 of 5 is 1, right? That's the use here. Okay, so same thing. If we do this, a to what exponent would give me 1? Well, again, I could just rewrite the right side as a to the 0. That will give me 1. So therefore, this would have to be a to the 0, which means the result, log of any base of 1, the result would be 0. You could also, if you had numbers, you could use the change of base formula that we saw last week, right on your calculator. What about log base a of a to the x? This is a useful one. Again, if we rewrite it, so this is, don't change, the base stays the same, right? So it's log base a, so my power is base a equals a to the x. Okay, so what do I have to put in here to make it work? X. So what this tells us is log base a of a to any exponent equals the exponent. That's kind of a big one. If we go up here, this guy is like a to the 1. So, and for the same reason, it worked out as a to the 1, right? So down here, I would have, it's the same idea. We just realized that it's not just 1. It's actually the exponent. It happened to be 1 in that first example. Does that make sense? So if you had log base 2 of 2 to the 7, the result is 7. Right? You don't have to go through all the steps of and use the change of base formula, that kind of stuff. Like, we're going to start to streamline this process a little bit now. Okay, next one's already in exponential form. So I'm going to rewrite it. And I'm going to, again, kind of just go down here and rewrite it in logarithmic form. So that would be, don't change the base, log base a of something equals log a the x. So if you want to just watch for a minute, if you don't really understand what I did, remember when we rewrite these things, my exponent becomes the result, and the result is what is applied in the log function. So, but the base doesn't change. So the base here was a, so the base is still a, but I took what we're looking for and put that in to the log function, and then the exponent becomes the result, right? That's what happened there. And so, what's the answer? It's x, right? How do I balance these? Put an x there. That's a big one. It's a lot harder. The one on the left, people will be fine with. The one on the right, people will forget. And I have a feeling that it might be important at some point, might come up on, some kind of major assessment or something. So, like, learn that one, or remember Like, you can always use scrap paper and rewrite this stuff and think about it. But that can be a harder one to rewrite because it's got to log in the exponent. Like, it's just unusual. So your brain flips and starts doing something weird with it. Anyway, any questions? Oh, forgot about this one. So we're going to take a look at this two different ways. One of them is going to go like this. I can simplify inside. Do you agree? 10 to the 2 times 10 to the 3. So this is log of 10 to the 5. And what does that equal? See, we forgot already. 5. Why? Because this is base 10. Right? It doesn't say it, but it's base 10 because there's nothing there. That was log base 10 of 10 to the 5, so that's 5. That was one of the things we just learned. Do we understand that? Okay, so then the other way we're going to do is we're just going to, wonder. Suppose I'm going to take, because this is something that often would be true, or something along these lines would be true, kind of like distributive property type thing. Okay, where if I'm kind of doing it to two together, can I do it to each of them separately? Does that make sense? It's like the distributive property that you would see in algebra. But we don't know that this, like, I didn't do anything. I just split them up. Like, we don't know. We don't have a rule for this. But what would happen? So how do I evaluate log base 10 of 10 squared? Chad? It's 2. And the other one is 3. And what is this supposed to equal from when we did it the first time? 5. Does anybody know any kind of operation that I could put between the 2 and the 3 to turn it into a 5? Chad, what do you think? Oh, nice. I didn't think about that one. 2 plus 3 is 5. So that worked. Is that a fluke? I think if you think about it, if you sort of like think about what logs are and with exponents and that kind of thing, and like why, we added the exponents here, and then really what we're doing is adding the exponents there, right? Like that's what, so you can kind of realize that it makes sense, but we're going to prove it as well. Yeah, but sometimes we think things are that we can do things when we can't. So for example, the square root of 5 times 3 does equal the square root of 5 times the square root of 3, but the square root of 5 plus 3 does not equal the square root of 5 plus the square root of 3. So like some properties are true for multiplication but not addition, or vice versa, or that sort of thing, right? So we need to know when we can do what. And the same for exponent. I mean, square roots are just exponents, so it's the same for exponents. When you're multiplying powers with the same base, you can add the exponents, but not if you're adding powers with the same base, right? So this is the same idea. You are multiplying here, so then we can add. It does work. Okay, but let's prove it. So this is a neat little proof. And we're going to start with let x equal log base a of m. And that means if I rearrange this, I get a to the x equals m. And let y be log to base a of n. Therefore, a to the y gives me n. And so I'm going to start with this. This isn't really following from there. I'm just using the space on the page. I'm going to start with this. M times n is a to the x times a to the y. So left side is mn, right side is a to the x, a to the y, which is a to the x plus y. Oops. I did these separately. You could, you don't have to do this as left side, right side, but I'm going to take the log of both sides. Okay, log base a of both sides. So log base a, mn, equals log, base a of a to the x plus y. And what did we just learn? Log base a of a to the x plus y equals? Not 1. Because the exponent's not 1. You're on the right track. So what is it, Brandon? X plus y, right? So log base a of a to some exponent equals the exponent. So what do we have? We have log a to the m times n, that was the original thing, equals x plus y. But what is x and y? X is log, this is from over here, right? What are x and y? That's what we let them represent. So log base a of m plus y, which is log base a of n. So equals log base a of m plus log base a of n. That's our rule. And it goes both directions. We don't just use it to expand, we can also use it sometimes to simplify. This is like an easy little proof. You just have to know where to start. Once you start with these things, then it works itself out pretty easily. Everybody okay with that? The only reason why we look at this is so that you know why, so that you're not just blindly following these laws that you don't understand or you have no idea whether or not they're true. You probably saw something similar with exponent laws, or with exponent laws it's a little bit easier to sort of convince you. Okay. I don't have quite as much space to prove the quotient law, so take my word for it. It's basically the same. Except you would end up subtracting. Just like power laws. Multiplying with the same base, you can add the exponents. Dividing the same base, you can subtract the exponents. Same thing with logs. Oh, is that okay? Everybody got that? Okay, so the power law, we're going to basically, or start with something very similar. Let x equal log base a of m. And so same thing, then m is a to the x. Everybody okay? Just want to make sure you caught up. So I'm going to start with that log base a of m to the n, but I'm going to replace m. So I get log base a of a to the x all to the n. Is that okay? I just subbed in for m there, right? You could just watch if you want. I mean, you could write it down after. I don't know if you need really to have this written down. Okay. Oh, so now I can log base a of a to the x times n. And from one of our earlier rules, how can I evaluate that? See when I said this was an important one? So equals xn, good. Do you agree that that's also equal to nx? Nothing weird there? And what is x? X is the log base a of n. M. I say n. So look at what we started with. Log base a of m to the n. So like, examine that for a minute. This is another big one. Like, what's happening here? Like, how could you use this? What's the purpose of this? What's the function? If you're evaluating logs or trying to simplify them or rewrite them or something like that. Sometimes I can't tell if a question's too obvious and nobody wants to answer or too difficult and nobody wants to answer. Which one is this? Anybody want to tell me? Or a bit of both? It's new, it's different, I know. Okay? Yeah, so you can take that exponent, and these aren't the same base anymore. It's not log base a of a, it's log base a of m. Log base 2 of 3 to the 6, instead of doing 3 to the 6 on my calculator, which give me a really big number, I could take the 6 out, multiply. That's interesting. And very useful. Let's see an example of that. Oops. So how about this? Log base 2 of 16 squared. So this will work out because everything is powers of 2. It'll all work nicely. And you could do 16 squared and then figure that out. Or you can do 2 times the log base 2 of 16. And so what we've been doing with something like log base 2 of 16 is, we let it equal x, we rewrite it in exponential form, and then we solve the exponential equation. You only have to do that if the instructions say to do that. I could see on a test that a question might say, it was supposed to be on the learning goal today, rewrite in exponential form and solve the exponential equation by equating the bases, right? This is what we call it. So if you're told to do that explicitly in the instructions, you do that. Otherwise, you just evaluate this. 2 to what exponent is 16? It's 4. If you can't do that, I want you to get to the point where you start seeing it that way. After you've been working on this for a couple of days, just like if you saw 2 to the 4, you'd be like, oh, it's 16. You just know it. Your brain just knows it. Because your brain knows how to read exponent notation. But our brain doesn't know how to read logarithmic notation at first and eventually gets there, and you start to just see the answers. Right? So if you can do that, do that. If you can't, I guess use your calculator or on a scrap piece of paper, rewrite it. Don't forget about the test where you're not allowed to use your calculator. You wouldn't be able to just use the change of base form there because, well, if you didn't have a calculator, because you need a calculator for that. Everybody good? And that's easier probably to evaluate mentally than doing 16 squared and trying to figure out what power of 2 that would be, right? If I do log base 5 of 10, that's log of 10 divided by log 5, I get a decimal, a nasty decimal. And you're going to get the same for log base 5 of 12.5. 2 nasty decimals. However, what's another way that I could evaluate this? Maybe using one of the laws we just learned. I don't know. What do you think? Yeah, and backwards from the way that we saw it before. So how, Vivian, can you tell me how I would write that?
Log 5, bracket 10 times 12.5.
Nice. Ten times 12.5 is 125. Log base 5, 125. 3. 5 to the 3 is 125. That is the kind of thing that you should be able to do mentally. You got to know that law. You have to be able to evaluate log base 5 of 125 mentally. That's the expectation. How high should you be able to go? That's always going to be the famous question. How many of these do we need to know? I mean, I'm not going to give you anything crazy. What's 5 to the 4? Even that's maybe starting to get a little bit unfair, but 625. Most people probably do know that. Beyond that, I don't think I would ask. 3,125 would be the next, but I wouldn't ask you to do that. Same thing with base 4, 4 to the 2, 3. You should be able to do for sure. 4 to the 4 probably, which is same as 16 squared. Anyway, but nothing crazy, right? And then obviously 2s and 3s, you can go up a little bit further. Okay, try another one. Ooh, this one's really tricky. So it's going to be log base 3. This is the quotient law. Same base. It's interesting, both of these are written the other way, though. Like with exponent laws, you wouldn't usually see it this way and then expand it and do it. See how we're kind of using it backwards from how you would use an exponent law? And it can go both directions. There could be times where you would want to turn that second step there into the first step for sure. So log base 3 of 27, and again, it's 3. I always think about how people who don't really understand math look for patterns where there are none. Things like this, like, oh, they all work out to 3. That's it. That's easy. That makes it easy. Every time it's just 3. Yeah, that's one way of looking at it. There was a movie years ago now with Jim Carrey. I think it was called 23. Has anybody seen that? No? It was a bit of a lesser known movie. I really liked it. It was a little bit about math and numbers. It was kind of about that, finding patterns where there aren't any. And he kind of loses his mind, and it's Jim Carrey, so he's good at that, right? Anyway, I would say it's an interesting movie to watch. Okay. How about this one? So this is where, when you practice, you hopefully start to get a sense of like how to approach a question like this. If you were doing it on the no calculator test, how would you do it? Okay. So there are a couple of ways that you could do it, but we're going to do it this way. Of 8 to the 1/3. Like you could evaluate 8 to the 1/3, but we're not going to. Which equals 1/3 times log base 2 of 8. Which equals 1/3 times log, like this step is a little bit, base 2 of 2 cubed. Why do I keep doing that? And so log base 2 of 2 to some exponent is the exponent, which is 1, right? Like I could have just gone straight from here to here. There's no reason why I really included that middle step, except for just to sort of show how there's lots of different ways you could continue to rewrite these things and use these laws depending on how you see it. Everybody okay with that? Like for that matter, or the cube root of 8, we kind of just know is 2. So this would also be log base 2 of 2, which is 1, right? Like I know that there's kind of a shortcut, but this one shows the use of all of those laws a little bit better. Okay, a couple more kind of quick examples. Show the ways that we could use these things or the kinds of questions that you might be asked to do. Compare the following functions. If I think about these as graphs, f at x, g at x, what are they? One of them has a horizontal compression by a factor of 100. And the other one has a vertical shift up 2. Is that right? So this is the same as log to base 100, or sorry, not base 100, log of 100 plus log of x. And what is the base? It's 10, right? Both of these are base 10. What is log base 10 of 100? In other words, 10 to what exponent gives you 100? 2? Oh my gosh. They're the same function. Wouldn't necessarily have expected a vertical shift like that would be the same as a horizontal compression. Does that make sense, everybody? Don't write this down. I just want to show you something because this is from grade 11. And I think a lot of people don't get this, and I love it. So I want to share something I love with all of you right now. When you do exponential functions in grade 11, there's this thing that happens, and some people get it for sure, and like they see it and maybe don't get it, but believe it or whatever. But there's it's neat how there's so much of it. So if I have, let's see if I can just do this on a whim, 2 times 2 to the n. Or another one, y equals 2 to the n plus 1 or something like that. So again, it's like a horizontal shift versus a vertical stretch. But they're the same thing. And there's like an infinite number of these when you're looking at, there's so many times when you're looking at exponential functions where this would occur. Because this is like 2 to the 1 times 2 to the n. So I can add the exponents, right? So it's 2 to the n plus 1. So it's the same thing, right? And so adding a vertical stretch or compression that has the same as like the base of the exponent. Like if I was multiplying by 3, it wouldn't work. But if I multiply by 2, then you get all these parallels of different functions that look like they have different transformations, but they're actually the same. We saw a little bit of that in this course, but not enough maybe. This is a neat way of looking at it. And so the same would be true for logarithmic functions, right? But again, maybe we don't see the notation quite the same. But this happens so much. And quadratics too, like because you can factor out sometimes a horizontal compression or whatever, and so. Okay, last example. This is just like a math class question. Like, can you use the laws or the rules that we just learned to rewrite this? And I think, at first glance, you wouldn't even, it's the kind of question where you wouldn't even really understand what it's asking you. But again, this really shows I couldn't use a calculator for a question like this. I have to just use the laws. So again, I would expect a question like this on, the quiz later this week, or even the exam or something like that, right? Okay, so log, it's always nice to get, if it's like the fifth root, to get that out as an exponent. So x cubed y over z squared all to the 1/5. Oops, log base a. And what was one of the laws that we learned where the base doesn't have to be the same, like the log base? You understand what I'm saying? It's not like log base a of a, log base a of anything. And I can use the exponent, like how could I use that here? Any thoughts? How could I use the power law here? Sam? Thank you. And now I can split this up as 1/5 times log base a. So it's something divided by something. So x cubed y minus log base a of z squared. Need that in brackets times the 1/5, right? Because it's 1/5 times everything. And then I can split up that first part as well. Log base a of x cubed plus log base a of y minus log base a of z squared. You could have done that in one step. And this is what the question means, expressed in terms of log base a of x, log base a of y, log base a of z. But we have to take it one more step and just get the rest of the exponents out of there. So now I have log base a of x plus log base a of y minus 2 log base a of z, right? So I have to take it all the way till I have just log base a of z, y, and x. Does that make sense? That's what that question is asking you to do. Make sure you understand not just how to do it, but what the question is asking and what would be a full, completed solution to a question like that. I wouldn't want anybody to lose marks just because they didn't know they had to take it another step. Any questions?